Recording in progress.
So today we are discussing a little bit the Lorenz equations. So those equations were introduced by Edward Lorenz in the 60s. And so Lorenz was working on the forecasting, weather forecasting. And so he came up with those equations from Navier-Stokes. And so as we will see, um, so those equations are very well known and very studied because they have the solutions have a chaotic behavior. And so actually Lawrence was very surprised when he found his results, and he thought that it was a numerical problem because the solutions have had a unpredictable behavior. And in fact, so it was not an error. It was actually the system who was chaotic. So now the first thing to do is to look for a stationary solution. So we get 0 equals sigma y minus x, 0 equals rho x minus y minus xz, and 0 equals xy minus beta z. So this gives x equals y, 0 equals x times rho minus 1 minus z, and 0 equals x squared minus beta z. So we can see that 0, 0, 0 is a stationary solution. And here, instead of x equals 0, we can choose z equals rho minus 1. And then to have this one equals to 0, we'll have x squared equals beta rho minus 1. So we see that this is only possible when rho is larger than 1. And so for rho greater than 1, so two new stationary solutions appear, which are, let's say, square root of beta rho minus 1, square root of beta rho minus 1, and rho minus 1, and the same with a minus here. This is called a pitchfork bifurcation, but it's beyond the details to study that theoretically is beyond the scope of this introductory course. All right, so now we're trying to do a local stability analysis. So we are going to write the Jacobian of our matrix. So if we look at the Jacobian matrix of these functions, we get J is sigma minus sigma 0 rho minus z here minus 1 minus x, and y x minus beta. So let's look at the stationary point 0, 0, 0. This gives sigma minus sigma 0, rho minus 1, 0, 0, 0 minus beta. And so the eigenvalues are then minus beta, and we'll have 0.5 of, actually it's that, right? Okay, so yeah, because I made a mistake here. So this gives minus 1 plus sigma plus minus square root of 1 plus sigma square minus 4 sigma one minus rho. Okay, so when we look at those one, uh, we can see that when rho is greater than 1, it's a saddle point. And when rho is less than 1, it's a stable node. So finally, for rho less than 1, 0, 0 is a sink. And for rho greater than 1, 0, 0, 0. So it becomes unstable and it's a saddle point. All right, so next we are going to evaluate the Jacobian, but for the other stationary points which appear for rho greater than 1. And so, for example, this one, x star, so at x star, what we get minus sigma, sigma 0. So rho minus z is 1. Minus 1 minus x is square root of beta rho minus 1 and square root of beta rho minus 1, the same here. And here it's minus beta. So we want to write p lambda as the determinant of j at x star minus lambda I. And so we get that it is minus sigma minus lambda times, and a big parenthesis here. So 1 plus lambda times beta plus lambda minus beta rho minus 1. I close this parenthesis, and then minus sigma minus beta minus lambda plus beta rho minus 1. So now we are going to write p lambda as, so first, so to be minus lambda to the third. Then for square, what do we have? Lambda square. So if I do this one and this one, I got minus beta. This one and this one, I got minus 1. And those two, I got minus sigma. And that's it for lambda square. Then for lambda, I get so minus beta minus sigma beta minus sigma plus beta rho minus 1 then plus sigma beta all right, so there was a typo here. So uh, taking that into account, uh, this cancels here. Uh, this also cancels. All right, so we'll get here minus beta rho plus sigma. So let's write that here. And we obtain minus lambda beta rho plus sigma. All right, and then the last term will get minus sigma beta minus sigma beta plus sigma beta minus sigma beta here plus sigma beta here. That cancels. And minus sigma beta rho minus 1 minus sigma beta rho minus 1. So we get minus 2 sigma beta rho minus 1. And that's our V of lambda. So there's several ways to study that. Let's do one thing that is maybe simpler. What we can do is look at what's going on when uh, here it's a row. When row equals 1, then this cancels. So we get the lambda equals minus lambda of lambda square plus lambda sigma plus beta plus 1 plus beta rho plus sigma. Well, and then uh, let's compute the delta here. So the delta here would be this square. So sigma square plus beta square plus 1 plus 2 sigma beta plus 2 sigma plus 2 beta minus 4 beta rho minus 4 beta sigma. All right. And so we get this doesn't change. But here we'll get minus 2 sigma beta plus 2 sigma plus 2 beta minus 4 beta rho. Right, so I'm going to finish here. So finally, I'll get, let's write P lambda as so we'll get sigma minus beta plus 1 square. And then I'll get plus 4 beta minus 4 beta rho, which gives sigma minus beta plus 1 square plus 4 beta 1 minus rho. And this is not p lambda, of course, but it's the delta. Well, so when rho equals 1, this is clearly positive. Right. And so if I compute from that, when I compute the eigenvalues, so zero is a sorry, zero is a root, and the other two are real negative. This comes from the computation here, because I will get the eigenvalues, the roots will be minus this quantity plus minus square root of that square minus 4, this quantity which is positive. So I will get 3 eigenvalues. One is 0 and the two other one are negative. Okay. And all right, now from from this expression here, I see that the derivative of my p lambda is negative at 0, and p0 is negative if rho is greater than 1. So what's the picture here? So at rho equals 1, and so rho greater than 1, but rho close to 1. So at rho equals 1, uh, I have, so this is my p lambda for rho equals 1, and when rho becomes greater than 1, what we see, well, so I made no, sorry. So I'm not writing, so this was minus p lambda. So let's write p lambda. So in this case, we have that, that, and that. And when rho becomes greater than 1, what's happening is, so the derivative of at 0 stays negative from that, and the value at lambda equals 0 is this quantity, which is negative for rho greater than 1. So finally, I get something like that. And we'll see here that the three roots are real negative. So from that, we conclude that our stationary point x star is a sink for rho greater than 1 and rho close to 1. So the next question is, when does an eigenvalue uh, become 0, right? And so if we look at the p lambda here, again, we see that at 0, for lambda equals 0, p of 0 is not 0. So if p becomes 0 with 0 for a lambda with a 0 real part, it has to be with some lambda with this form. So the next question is there an omega such that p of I lambda equals 0? And if we ask that to be the first, the smaller row for at the when this happens, then we know that if we get some row like that, then we'll know that for 1 less than rho, then rho star, x star will remain a sink. And so by the other stationary point, it's the same actually. All right, so and we will follow up with that next time.